Hello and welcome back to Advent of Code 2018. We're on to day 5. And should be ready to go. Huh? Alright. Some people playing music on the street. I try and drown it out. Alright, let's begin. Day 5. Hello DJ, go yell at them. If I could speak Vietnamese, I would, but this is just normal. Everyone plays music on the streets loudly. What happened last time? Last time we had... Oh, so the theme of this year is time traveling. So we're going to different times and messing with time. Alright, so we're on to day 5. Alchemical reduction. Oops. You've managed to sneak into the prototype suit manufacturing lab. The elves are making decent progress, but are still struggling with the suit's size reduction capabilities. While the very latest in 1518 alchemical technology might have solved their problem eventually, you can do better. You scan the chemical composition of the suit's material and discover that it is formed by extremely long polymers. The polymer is formed by smaller units, which, when triggered, react with each other such that two adjacent units of the same type and opposite polarity are destroyed. Okay. Units types are represented by letters. Units polarity is represented by capitalization. For instance, R and capital R are units with the same type but opposite polarity, whereas R and S are entirely different types and do not react. Okay, fine. But does order matter? Because technically you could arrive at different results if you did them in different orders. Like B capital B B. No, that would be the same. Whoops. No. Yes. B capital B B capital B. So if you did the first two, and then the last two, you'd end up with nothing. But if you did this middle section, capital BB, oh no, you would end up with... Oh no, order doesn't matter. Yeah, okay. These puzzle designers really like that 70s Swedish... That's true. Is what I said always true? Does it always reside at the same... Yeah, it does. You can probably kind of prove it with an argument. I can't be bothered to do that. It's like, if there were two to choose from and you chose the other one, then you'd still get the same neighbor to the first. I don't know. Some hand-wavy argument says that it doesn't matter. And anyway, they haven't said anything about order, so you can assume it doesn't matter. Alright, so after all possible reactions, the resulting polymer contains 10 units. How many units remain after fully reacting the polymer you scanned? How big is this polymer? That's the polymer. seems rather simple. It's a question of size. Because it wouldn't really be simple if it was very, 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 very big. Now, how big are we talking here? This might not... No, this is quite big, actually. And it depends how you represent the data. Because if you reconstruct the string every time you remove 2 letters, then you're reconstructing a lot of strings, and that's a lot of work. So... we might need to think about a more efficient way of doing it than just doing each pair one at a time. Also, one obstacle at a time. Let's just get this into the... Yeah, definitely the basic algorithm is very simple. Okay, so that's the string. How do I make it bigger? There we go. Okay, so first, let's just read the input. Let's have a look at the size. Let's say line equals, let's call it poly equals f.readline.strip print length of poly 50,000. So let's, if we do the brute force way, you'd have a string of 50,000. You look through it, try to find a pair. If you find one, you destroy that pair, rebuild the string. You've cost yourself 50,000 steps of work. Then if you do that again, you've basically cost yourself 49,000 something or other, then 49,986 or whatever, and so on. So basically the amount of work you do is 1 plus 2 plus 3 plus 4 up to 50,000. Or actually skipping every odd number, but it doesn't matter. Which is roughly 50,000 squared. Halved. 50,000 squared and then halved. Half times n minus 1. 50,000 squared is like almost a billion. But we wouldn't actually be doing that much work each time because we would stop once there's no more. All right, shall I just try coding the basic algorithm and see if it actually works? All right, so while 1.25, that's quite a lot. But I don't think we'll get that far because I think we'll stop somewhere before we... There is actually a cleaner way of doing this though. Instead of rebuilding the string every time we find a pair, let's first scan the string, note down the locations of all the pairs we've found, and delete them all in one go. Then rebuild the string. That should... Now in theory that still takes up to 50,000 squared, but in practice, if it's suitably random, it will be much quicker. So let's say... while true. I equals 0, so we start from the start of the string. Or, let's say, no. Yeah, I equals 0. While I is less than length of poly. -1. We don't care about the last one because there's no neighbor to it. If poly, so we want poly I is not the same as its right neighbor, but it is the same when you lowercase everything. So poly I dot lower is poly I plus 1 dot lower. That means they annihilate. We want to store a list of deletion points. So we put deletion points dot append I or let's call it skip points. We skip these ones. And we'll do just make it a set. So those two we're gonna skip. And because we've skipped, we want to jump over I plus 1. So we do I plus equal 1. And then whether or not we did that whole step, we do I plus equal 1. So if this happened, then I will end up plus equal 2. So we skip over that neighbor because that neighbor should be annihilated, so we don't care about that one anymore. And we move on to the next one after. And if we don't do that, then we're just moving to the next neighbor. Okay. So this is always taking the first annihilation pair it sees. And it's putting all the annihilation or annihilated, whatever they are, chemicals, molecules, atoms, into the skip points. Now, we want to make a new poly equals this for I car in enumerate poly. If I is not in our skip points, new poly dot append r, and then finally we replace poly with a joined up the join of this list. So we basically cut out all the pairs we saw in that one pass. This should be more efficient. I think it'll be efficient enough to actually run. In theory, they could have made a really complicated string where it's kind of like the annihilation is in the middle, and every time you annihilate it, you introduce a new annihilation of 2 outer letters. They could have done it like that, but I don't think they will. In which case, you'd only find one each time. So after we do this... Oh! if there were no skip points, that means we're done. Break out of this loop. Print the length. Well, what do we want? Number of units left. Print length poly. Alright, see how long this takes. Done. 9116. Should have printed the poly as well. Should I do that? Let's just try the number. Correct? Time to improve the polymer. One of the unit types is causing problems. It's preventing the polymer from collapsing as much as it should. Your goal is to figure out which unit type is causing the most problems. Remove all instances of it. Regardless of polarity. Fully react the remaining polymer and measure its length. I see. So for each possible letter, we take that letter out from the starting polymer, do the process again, and whichever collapses the most, we want to say how short that polymer was. Okay, so basically we just do what we did 26 times. Okay. I don't think there's any clever way of getting around that. Okay. So that was part. Let's fetch the input again. So we want to do 4 in A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Let's also keep track of the shortest we find so far. Shortest equals, let's say, length poly to begin with. So for each car, so we can actually make this method. We can say define collapse. So instead of poly, we use P here. So then we just, this just spits out a number, the smallest number found, which is length E. So here we just do print collapse poly. Collapse. Check that still does the same thing. Oh. Does it, so this doesn't modify poly, does it? Let's just make sure it doesn't modify poly. No. Length poly. It makes a local copy of poly and modifies that. Good, okay. So we don't need to do this. Alright, so for each of those characters, we do collapse of poly.replace car with an empty string dot replace, oops, what am I doing there? Dot lower dot replace car dot upper with an empty string. So we're basically removing all lowercase and uppercase letters of that type. That will spit out a number, and we just want to say shortest equals minimum of that number and itself. So after we've gone through all letters, so we can just to see how far we're getting in this process, do that. And then finally print shortest. See, this replace method probably would be efficient to use here instead of skip points. You could just actually do dot replace, but with all possible combinations, BB, CC, DDE. Does empty space mean an actual space or just delete? So that's, if you don't leave any space between those quotes, then it's an empty string of size 0. So it's essentially delete. But you could put a space in there if you wanted to replace that character with a space. You could put any string of any length. And in fact, this can be a string as well. Which is why I was thinking you could use it up here. And I think it would already do all this. Just it would take the first instance. So that's actually code-wise more efficient. But I don't know whether it would be more time efficient. I think it'll basically do the same thing I did. It'll just find the first instance and in a single pass delete them all. Yeah, I assume that's what it does. I don't know if there's... yeah. Replace is a good method. Alright, so we've pushed down to 81716. I wonder... if there's any cleverer ways of doing this that's faster. I don't think so, because you can't predict what the string will look like after even a single pass. Like, they've probably constructed some weird situations where you get a sequence of cascading annihilations which only occur when you take the middle one, collapse the middle one, and then the next level, and then the next level will appear. So you can't predict ahead of time what will happen. This is kind of reminds me of automata theory. What's it called? Context-free grammars, regular grammars. 6890. Correct. I think that what I did where making a full pass was probably what you needed. If I did this... I mean, I could actually try this right now. I could try going to the very basic algorithm and saying, if I find a skip point, I add it to the list but then immediately break. So we only ever remove one at a time. Now let's try. See how long it takes. Probably put even part one. So now this is a whole order of magnitude slower because we're only doing one at a time. So basically we've multiplied the amount of work by the average number of annihilations that were present in one go. Because that means we're rebuilding the string that many times. Yeah, this is unrealistic. So it could be as many as... It could be something like 50,000 times slower, because there could be... Well, no. Oh, okay, we get the answer eventually, but that's pretty slow. So doing that for the whole alphabet is also very slow. Yeah, that was a nice problem, because I think for a lot of people that might be hard if they haven't worked with this kind of thing before. So Python is amazing with strings. Like, that's one of its strong points. It has all these useful methods for modifying strings. Can you tell it to output runtimes? Oh yeah, you can. You can use the timeIt library or various libraries. timeIt is built into Python and it's fairly accurate. It tells you how long it took. You can also tell it to run something like 1,000 times and take the average time and tell you how long it took on average to run a certain piece of code or a piece of methods. Okay. Day 6. Oh, is that Santa's hat? Yeah, it is. Chronal coordinates. Okay, we got something to do with two-dimensional map. That's nice. I like two-dimensional maps. The device on your wrist beeps several times, and once again you feel like you're falling. Situation critical, the device announces. Destination indeterminate. Chronal interference detected. Please specify new target coordinates. The device then produces a list of coordinates. Let's have a look at this list. Not that many, just that many. Okay. Are they places it thinks are safe or dangerous? It recommends you check manual page 729. The elves did not give you a manual. If they're dangerous, maybe you can minimize the danger by finding the coordinate that gives the largest distance from the other points. Using only the Manhattan distance, determine the area around each coordinate by counting the number of integer XY locations that are closest to that coordinate and aren't tied in distance to any other coordinate. Ooh, okay. Find the size of the largest area that isn't infinite. Let's have a look at the example. So if they look like this, so all these little a's are the places, are the spots which are closest to A. Then we've got B, C, D, E, F. Okay. And the dots are tied, so we discard them. A, B, C, and F are infinite. Alright, so how do we know something's infinite? If it extends as far as the edge of the grid, I would say that's infinite, because every coordinate past that will probably be tied to it. Yeah. So it's infinite if it meets the edge of the grid, and we can define the size of a grid. We can just say it's let's say 0, 0 to 1,000, 1,000. Or even less. 0, 0 to 500, 500, because it never exceeds 500. Yeah, okay, so... So how do we find the area around a coordinate? Basically, we just want to go through the whole grid and decide which... Alright, I mean, the obvious thing is, okay, so it seems a bit slow, but it might be fine. For each point in the grid, we wanted to determine which is closest, which of the locations is closest. So we just look at increasing rings around that point until we get to a ring which has one or more locations in it. If it's only one, then that means that one is closest. If it's 2 or more, that means it's tied, and we forget about that point because it's tied. We don't want any points which are tied. Just, it's not very efficient, but let's think. We've got 500 by 500 points. And in theory, you could, for each individual point, by doing this process, you could be going through the entire map of grid points. You would never really do that many. So in theory, it's 500 times 500 times 500 times 500. What's that? 500 to the power of 4. Okay, in theory it's that, but it's in practice it's nowhere near that. So it would be more like... I can't average it. It's a bit confusing because of the way this works. I think okay. That's one way of doing it. Maybe there's another way of doing this. Instead, for each location, we do that. We look at increasing rings around that. Basically, it's breadth first search. For each location, we look at all the points and we mark on each of them the distance. For example, for A, we basically do a breadth first search from A, and for each point we hit, we write down on that point, we make a note of the distance to A. And then we do that again for B. And we do that again for C. So what we end up with, every point has a record. I am so-and-so distance from A, I'm so-and-so distance from B, I'm so-and-so distance from C. Then we just go through each of those points one by one and work out, by looking at that list, work out who's the closest point. I think that's faster because, okay, in the worst case, we basically, for each of these points, we go through the entire grid. So it'll be 500 times 500 times this length of this list here. Which is, hello, Amaro. So that's more like 10, 20, 30, 40, 50, something like that. So it's like 500 by 500 by 50, which is 12 million. Yeah, that's fine. And in practice, it'll probably be shorter because we. Yeah, I think this is the correct algorithm. So So how do we put this all together then? All right. All right, so we've got oops. Okay, so we've got a bunch of locations. Is there another? I don't like calling them locations. Okay, fine, we'll call them locations. Alright, so let's say locks equals an empty list for line in f.readlines. Got xy equal int put them in the list of locations. Alright, so for each point, we want to keep track of all the distances to all the other locations. So we basically want a dist table that maps locations to so it'd be like it maps pair to for now an empty dictionary. And that dictionary will map locations to distances. Okay. So now we want to do basically a breadth first search process. So define BFS given a starting point. And this is going to return nothing. It's just going to update the dist table. So alright, the usual process. So we want a queue data structure. So we want start with the starting point, which has a distance of 0. Every single time I always have to think hard about how to write BFS, even though I've done it so many times. Okay, so while not q dot empty, current equals q dot get, let's say, distance current. So that unpacks the distance and the current. All right. Now we look at the neighbors. So for delta in. So I guess we want to consider all neighbors of the form. So there's 4 neighbors. We've got 0, 1, 0, minus 1, 1, 0, minus 1, 0. Neighbor equals neighbor x, neighbor equals current plus delta 1. Okay, so we've got neighbor. If it's within the bounds, so 0 is less than or equal to neighbor x is less than 500 and 0 is less than or equal to neighbor y less than 500. Alright, so we've got a valid position. Neighbor equals these packaged up. So this is a valid neighbor, it's in the map. Well, I can't think. By the way, when we... Okay, before I do any of that, when I unpack it from the queue, we need to update the dist table. So we say dist table start. So that gets us the mapping for that starting location. Now we want to say current equals dist. We're saying this node is this distance away from the start. That's what this does. Okay, we don't want to leave that step out. Alright, so now we've got this neighbor. If neighbor not in visited, we haven't seen it before, we want to put it in the queue. So we do queue.put. It's going to be d plus 1 neighbor. And we're going to add it to visited. So if we do this process, we should hit every node in the map and update every... Having trouble? No, not really. Seems fine so far. Then if we do BFS for one starting location, then this should be updated with the distance to every node from that starting location. So if we do this for every... Okay, so for lock in locks, BFS, run BFS starting from that location. just try doing that, see how long that takes. Ah, I'm splitting incorrectly. This should be comma space, because they've done it weird. Like that, comma space. Alright, now it's running this whole process. This is the most lengthy bit, so if this runs in a reasonable time, then we're good for the rest of the algorithm. It's taking a long time. Let's print the log. See how many it's getting through. It's doing them one by one. I guess that's to be expected. That's a reasonable rate. That's as good as I can expect. Alright, so... That's actually a bit slower than I'm expecting. 500 by 500 is not... it's alright. Fine. Can we... We could actually reduce that to 400 because it never goes beyond 400. Yeah, let's do that. Just save a bit of time here. 400 by 400. All right, now. We're not quite done because the problem is we need to discard all those which have infinite area, i.e. all those which are whose area touches the edge of the map. That has to kind of be done here because we don't keep track of those. No, it doesn't have to be done here. Okay, so we've got the right data. Now, we want to say... Okay, maybe the way to do this is we need to keep two variables. We want a counter. So let's say 4. Every position in the map. So you want to say for x in range 400. For y in range 400. So we've got a position. Right, now so area is going to be a counter that counts for each location how many nodes belong to that location. And a node belongs to that location if that location is the closest. So we want to say For this pause, we want to look at the table we've built, and we want to say which of these locations is closest. So for now, the closest... Oops. Okay, for now there's no closest. We want to say for lock in locks, the distance is going to be use the dist table for that lock, for that pause. So that gets the distance. And if closest what am I trying to do here? Oh, okay. Closest D is none. Closest lock is none. So if closest D is none, or D is less than whatever the current closest is, then we update. So we say closest D is D. Closest lock is lock. Okay, I could have used a minimization there, but whatever, we'll do it the old-fashioned way. Now, we know what the closest lock is to that XY, so we simply say area for that lock plus equal 1. We've just added 1 to that location's area. So if we do this whole thing, we now end up with a list of areas for each location. Let's see what this looks like. So we have to do all these. But we're not done yet because we have to get rid of all the infinite ones. What? What the heck? How? What happened there? Ah! Closest lock. Whoops. Do that all again. Not lock. So it was just always using the last lock in the list. So we have a counter. We've now hopefully correctly found the area of each location. Let's see if the numbers look sensible. So for example, this location has that many spaces which are closest to it, and so on. Seems quite big, but no. That seems about right. Okay. Now the last thing we need to do is get rid of all the infinite ones. So we want to say... we want to keep track of all the infinite ones. So say infinite equals set. So during this process, we will know if a location is infinite if it's on the boundary of the grid, because that means it'll just extend off forever. So when we get to this bit here, if x is 0 or x is 399 or y is 0 or y is 399, that means we're on the boundary. We've discovered that closest lock is actually an infinite area. So we say infinite dot add closest lock. Okay. Okay, finally, how do we put this all together? We basically go through this counter, delete all the guys who are infinite, and see what's left. So, for L in infinite, delete counter L. Alright, what do they actually want us to do? Find the largest area that isn't infinite. So it should just be whatever's largest left in this counter and now is the largest. So print max counter.values. Oh man, okay, there's numerous things that could go wrong here, but the numbers are looking okay. This rests on my assumption about the infinite thing. If it's touching the boundary, it's infinite. Is that strictly true? No, it's not. I can draw a picture of why it's not, but it's a bit hard to explain in words. Object does not support item deletion, really? Oh, not counter. We want to use area. Whoops. I'm trying to delete a type. And yet we should be using area.values there. Area is the variable name. Alright, I've just realized this is not completely correct. You can have a location whose area touches the boundary, but there's two locations either side. And in the true infinite grid, those two locations will sandwich it, but this occurs outside the bounding box. So, in our restricted grid, it could look like this guy is touching the boundary and therefore is infinite, but actually he's sandwiched by two others and will eventually be enclosed by two others. So, either we need a bigger bounding box, or I need to use some sort of proper mathematical determination of whether an area is infinite or not. 4787. I can try this, but I don't think it's correct. No, it's too high because I'm including some which are actually infinites. No, hang on. It says it's too high. But if I was including... Interesting. It says it's too high. But what I was saying was if... I mean... I'm discarding some locations because I think they're infinite, but they're not really. And if I were to include those, this will only make the values go higher. So, wow, this is really confusing. Maybe I just need to actually draw a physical picture of what this looks like with what we have here. So if I make a grid, okay, so we've got a grid. So here, when we find the closest location, let's say for I lock in enumerate locks, closest lock equals lock. Let's use I, the index of the lock. Okay, so when we've done all this, we want to also just put it in our grid so we can build a picture of it. So say grid, y, x equals closest lock. Right. For row in grid, print row. It's gonna look a bit. Just see what it looks like for now, but it's not going to be aligned correctly because some of them are single digits, some of them are double digits, so we need to standardize it if we want to make it visually look right. This is kind of what it looks like. That kind of looks right. You'd expect a bunch of diamonds. No, not diamonds. Wait, what? Okay, no, this doesn't. Oh no, it's because of the spacing. It's always going to be weird because I need to, Wait, this doesn't look good at all. Why is it like... Oh, there's another thing I forgot. Ties. I didn't handle ties. Damn it. Ties have to be discarded. So if a location has two closest locations, then we have to ignore that location. That's very important, okay. But I'm not sure if this picture looks correct. No, that's sort of correct. But they shouldn't be rectangles, they should be diamonds, shouldn't they? Yeah, I don't like the shape of these. This is just one gigantic rectangle. And this is one big rectangle, but they shouldn't look like rectangles, they should be diamonds. Like this kind of diamond. Under the Manhattan metric. Yeah, this is all wrong. Why has that happened? Something to do with the way I'm doing the BFS? Let's have a look again. So I use the 4 neighbors. So it goes right, left, up, down. So you would expect it to expand in a diamond shape. So the area for 1 and the area for 30 shouldn't meet on a straight edge like this. It should be kind of a jagged edge where one is to the left and one is to the right, and they're both forming diamonds. Why is this happening? What is 1? 1 is this one, 4240. So it's saying that all these places are closest to 4240, and all these ones are closest to whatever 30 is. Which is like, This one, I guess. 63.75. Yeah, they shouldn't meet like at a straight edge like that. Alright, one thing at a time. First of all, let's get rid of all these ties because they're wrong. This is a bit of pain. Oh man, what time is it? I'm supposed to go to the gym. But it's Friday, it's usually a very busy gym day on Friday. Maybe I'll go tomorrow instead. Won't be too busy. I think my whole process is not good enough because it's... We need something smarter, but we need to know ahead of time which ones are the infinite ones, because these are the getting in the way. Like, we can't work, like, we can't just keep taking a bigger bounding box to work out what the total size is, because some of my diamonds are getting cut off by the edges of the bounding box. We could... Well, let's first handle the ties, because that's an obvious issue. So, ties, how do we deal with that? So we say... We need to... Oh, I need to change the way I do this, so... After we found the closest distance, we then need to go through each of the locks again, count how many are at that distance, and if it's more than one, that's a tie, and we say that doesn't count. That's the, I guess the way we have to do it. Okay. So let's change the way we do it. Let's take that out. We say for, okay, we don't need to index these. We just say for lock in locks. D is the distance. If closest D is none or D is smaller than that, blah, blah, blah. We get the closest distance. Okay. Now we know what the distance is to the closest lock. Now we do this again. But we say closest lock equals none for lock in locks. If this table lock pos is equal to that distance we're looking for, then we have two things to check. If closest lock is none, closest lock equals lock elif. If we already found a closest lock before, now we have a problem. We have a tie. So we say just signify this with a -1 and break out of the loop. Okay. So at this point, either closest lock is alright, we want to stick to using enumeration here. So if closest lock is -1, continue. Right. Now we just continue as normal, and then we do that. Okay, let's just print what this looks like. This might Alright, this will handle the ties. Let's see at least that we're getting rid of those ties. So on the grid, at every boundary, we should see -1s. Let's go back to the top. Yes. We got -1s. Alright, one problem resolved. Okay, the other thing is, why are they still rectangles? Is it... Why have you done this grid a bit weird? None for X in range 400. For Y in range 400. Alright, the other thing I think we should do is increase the size of the bounding box, because if we go... We're going from 0 to 500. Let's go instead from minus 500 to 1000. That adds a kind of an extra 500 each side. I think that's enough for each diamond to get closed off. Each non-infinite diamond to get closed off. It'll be a more runtime, but I think that'll make it... That'll make it clear whether something's infinite or not. That gives enough time for every diamond to get closed off, if it's ever going to get closed off. If I reason that out correctly. So let's say min val equals, I don't know, minus 500. Max val equals 1000. So everywhere we're using coordinates, we need to start using this. So we say... Okay, if neighbor x is less or equal to min val Okay, so that's safe there. And then down here we need to do for x in range min val to max val. Same here. Same here. Same here. And then down here, if x equals min val or x equals max val minus 1 or y equals min val or y equals max val minus 1. Okay. I don't know. Try that. We're gonna have a bigger grid now. This is gonna take ages. Oh god, look, it's already taking too long. But just one BFS? No. This is no good, is it? We need to completely overhaul the algorithm here. How do we know whether something's infinite or not? If... How goes the grid thing? It's a bit slow. Not... Well... It will run in time, but it's a bit slow because I've increased the size of the grid to like 1,000. I think I need a cleverer way of knowing if something's... if a location has an infinite area around it or not. Right now I'm just kind of taking a big box, computing its area and seeing whether it hits the edge or not. I think that's too inefficient. I think we need some smart way of knowing ahead of time. Wouldn't it be infinite if there were no points to whichever side? Yeah, something like that. That's probably the insight. I just need... Certainly if it's the highest most point, or the rightmost, or the leftmost, or the bottommost, that'll mean it's infinite. If it's... But you can have situations where... I don't know, we'll try running this with this big box and see if that works. I don't like the look of this grid though. Because we're getting rectangles instead of diamonds, which means I've done something wrong. Is there a way to speed up this BFS as well? Probably. We can probably halt early if we kind of closed off on all... If we encounter... Well... It's a bit of a mess. I should run it on the test example they've given, see if we can... Because then it will actually run faster and we can probably debug it. The test example they've given is 6 points. And they're all within 1 to 10. Where are we in this list? 3, 4, 5, 1, 2, 3. Just over halfway through the list. I need to think about this geometrically. So each point has increasing diamonds around it of distance. And these diamonds... Memory error. We're using too much memory now. Visitor.add neighbor. What? But that data structure should be refreshed every time, so... So we shouldn't be running out of memory. What? The most this should ever have is... Alright, whatever. I mean, okay. Let's go to the basic example that they've given in the problem. So because we're still using this massive grid. All right, let's stop. All right, so the problem they've given is 1 to 10. So let's go from -10 to 20, just as the bounding box. Okay, so that's what it looks like. Ah. Now I realize they do look like rectangles sometimes, because when two diamonds intersect, they intersect along a straight edge. That's where the straight edges are coming from. So that's not wrong. That's actually sort of correct. What doesn't look correct is here. Why... We've got 2 here and we've got 0 here. Why is there no -1 between them? There should be a... Alright, well anyway, 17 is the answer we got for that. Correct. 17 is the correct answer for this. So maybe we're actually on the right lines. Now we just have a memory problem because I'm using such a big box. Oh, I see. Yeah, no, that's right. Sometimes there's no tied boundary. Sometimes there is. You could have okay. If you had 2 locations which are an even space apart, then there would be a hard boundary between them which is shared. And if they were an odd space apart, then there may be... there's no real shared boundary between them. They just meet up. That makes sense. So sometimes you have straight edges, sometimes you have diagonal edges, sometimes you have shared boundaries, which are -1s, and sometimes you don't have shared boundaries. So yeah, everything I'm seeing is fine. It's allowed. Okay, we're getting somewhere. And we got the right answer, which is 17. And does the picture look roughly like their picture? We have to look at the 0 to 10 bit. So that's... Wait. We've gone from -10 to 20. What? Hang on, something's wrong again. 0. 0's here, 0's here, 0's here, and 0's here. What the heck? That's wrong. 5. Who's 0? 0 is 1, 1. Why? So it should be up in the corner here somewhere, but it shouldn't be... Oh god, what is going on here? Like, these points here shouldn't be closest to 1, 1. Why is this happening? Oh, okay, this is so confusing. Yeah, look, we've got one over here and one over here. Why is that happening? Something is some sort of it's something like it's rolling off the edge. Somehow I'm going off the edge of the grid. I'm trying to access. Let's have a look how we're accessing this grid. Grid Y X. Y is in this range. X is in this range. So it should be minus 10 to 20, minus 10 to 20. Oh, oh, of course. The coordinates, damn it. So, how do I... Yeah, the way I'm accessing the grid is wrong. Because I'm taking like -5, but of course this starts from 0 in the grid's coordinates because it's shifted. Okay, fine. But it doesn't matter so much because this grid was purely for our visual benefit, so maybe we can just discard the grid. We got 17, which is the correct number. The area seems to be correct. So let's hide the grid for now. So let's assume we're getting the correct answer. We just got to solve it and not use too much memory now. Alright, so get rid of the grid. Don't worry about the grid. So we're using too much memory. That's really strange. Is it because is it keeping all the previous visited data structures? Can we tell it to deconstruct visited upon exiting? I thought it would already, but then a garbage collector's probably not collecting them up. Can we not just say delete visited afterwards? I think they're not, for some reason they're being kept in memory, because the most it should ever add is 5,000 would be 1,500 by 1,500. What is that? $2 million. That's not too bad. Let's try that, see if that changes anything. Deleting visited. I would have thought it would do that anyway, but I don't really know much about Python's memory management. Because the only thing we want to update is this dist table. This table is pretty big, but I wouldn't think that's the problem here. Okay, so the other thing I can do is I can terminate this early when we realize we've reached a point which is closer to some other locations. How do we do that? We say if I think this table is inverted. What we actually want is a mapping from every location to we'll see if this runs, but I think we actually want it the other way around. We want a dist table which maps every location to a set of distances to each of these points. Basically the opposite way around of this. Yeah, because I'm doing this in a really weird way. It's correct, but it's just kind of... going through the locations is a bit weird. We should... like, when we get to this bit here, we've got a position. We then just want to pull up the list of locations and their distances to that position. And then see the closest ones. So closest D would literally just be min of those values, instead of this thing we're doing, which is awkward, and this thing. Okay, so if this runs out of memory, we'll switch to doing that. I don't know why it's running out of memory, though. I think the memory is... Visited holds 2 million things. This table holds more than 2 million things. Something like 100 million things. So the memory issue should, if anything, it should be with this table. But it seemed that it was with visited, which is weird. But I'm now kind of garbage collecting visited each time. And this is a tricky problem. You really have to think geometrically about it. Memory error, yeah, okay. Let's make this let's do that then. So this table, let's change that to be so it should be should be an empty hash table, and for x in range min val max val, or y in range min val max val, we should say dist table And for lock in locks, we should say, so dist table for that coordinate is an empty dictionary, and now for each location we say this table for that location is... Oh my god, I'm so stupid. We don't need to do this BFS at this point right here. We know what the distance is. We don't need to do BFS. We just say it's literally just the... It's... it's this. It's... So that cuts out this whole thing. Why did I do this? I had something else in mind when I wrote this BFS. It's completely not needed. We know what the Manhattan distance is at this point. We just say it's lock. So it's going to be absolute value of lock 0 minus x plus absolute value of lock 1 minus y. Right. So now we have a dist table which maps an xy coordinate to a dictionary, and within that dictionary, every location we've marked its distance. Okay, so we just run that, get rid of this whole BFS thing. Now, when we unpack this, instead of all this, let's say... Can't believe I went down the BFS path. Alright, so we say... Pause. Alright, so we've got the position. So closest D will be the min of dist table pause. That brings up the dictionary dot values. So that's the closest amongst any of the location's values. All right. Now, we want to say if there are at least 2 locations at that distance, then this is a tie and we skip this one. So if dot count, is that a thing? Dot count closest D is greater than 1. No, it's not dot count. Dot, so we've got list. Dot. Is it? I thought there was a method for counting how many things appears in a list. Python list count. Yeah, dot count. Is that a list? No, probably isn't a list. We have to cast it to a list. Well, it might be, but I think at compile time it doesn't know. Alright. We skip this one. Alright, so at this point we know there is a unique closest D. So we say for location and locations, if equals closest D, and now we can say area is 1. Alright, and then we now to do the infinite check. If we are at the boundary, infinite.add break out of this. So lock is still pointing to the closest one. Went from a thing that took like a total of 10 minutes to this monster. Yeah, this whole BFS, I don't know why I went down that path. Because there's no obstacles. When you don't have any obstacles, then you don't need to use BFS. You know how far X and Y are from each other. It's just literally just a coordinate distance. So if equals closest D lock that should be it. Let's try running it. It'll still take a while, but shouldn't get a memory error. Can we have some indication of progress? Can we say if x%10 is 0, print x. That'll give us an indication of how many x values we got through. Okay. Still gotta wait for that to go to 1,000. Nah, it won't take too long. Thing is, we don't even need this table. That is a standalone formula. We could just do that, copy that formula into here. We don't need to reference this table. But the good thing about this table is it holds it all in memory, so we don't have to keep calculating that formula. So I guess it's not harming us to populate this table before using that, but so now we've populated this table. Now, I'm going back to going through each grid location, but finding the closest lock. So it's going to take the same amount of time. I should really put a... say 100. But we'll just wait. There we go, 4771. Oh no, I don't think this is right. 47. Because they said it should be higher, didn't they? Or... Oh, it is right. No, they said it should be lower. We weren't actually far off with the original number. Because the algorithm was mostly correct. We were just including ties. But then when I discarded the ties, we were just using too much memory. Wow. That was a lesson learned. Just don't always jump to BFS. It's tempting. BFS is fun. Yeah, off by 16. Actually, it wasn't just because of ties. I think it's because, okay, I had a smaller bounding box, 0 to 500. So most areas were getting closed off within that bounding box. But some were just quite reaching the edge. And were getting closed off outside that bounding box. So I could have increased that bounding box just a little bit, like 10 to 20. But I didn't know what the correct amount was, so I increased it by 500 either side. Which made me almost 100% sure that any area would eventually get closed off if it's ever going to get closed off. And anything that's still protruding outside that box must be infinite. That was my theory. And maybe that can be proved mathematically, I don't know. But that bounding, going to minus 500 to 1,000 was just too big in terms of memory. But... yeah, but yeah, that queuing and that BFS, like, oh, I feel dumb for going down that path because it's... You use BFS when you're getting around obstacles, but if you are just talking about raw distance, you know... See, the thing is, I don't even actually need this thing here. That formula there is all we need. If I were to just copy that... and just by 16 gigabytes more RAM. I don't think it's even RAM. I think Python kind of has some limits, built-in limits to what it will allow, and you can import sys and you can actually overwrite those limits to bigger limits. Last time I did that, I actually crashed the stream and my computer. I had to reset the computer, so you're not supposed to do that. I do that when I do online competitions because I'm not using my own computer for that. I'm using the system's PC, so I do often override the system limits because it usually works. Like set recursion limit to 1,000,000 or something because we're using the online server and they just have powerful enough computers that you can do that. But yeah, you're not supposed to mess with sys. For good reason. See, I did actually once crash a stream doing that. But yeah, as I was saying, you don't even need this disk table. You know this is a static formula. So this could just be inserted to... This values thing is basically that static formula computed over all the locks. That could be done right here. But there's no harm in building this disk table. It's actually kind of nice because it means we've now... all the memory we ever gonna need is there, right there in that disk table. So it kind of reserves that space. And we know if we manage to finish that disk table without crashing, that means that's fine. We never need any more space than that. I guess that's kind of nice. But yeah, it's interesting that I think where do we draw the line? Where do we draw the bounding box? I'm not sure. That it's. I think I might have had the right idea here. I think 500 either side is probably the right amount, because if you have a diamond which starts at the bottom of the bounding box, I can't do this without opening up Microsoft Paint and drawing diamonds, but yeah. I think there's some argument there that I think 500 is the right amount either side. If they were to construct some really horrible example where you have one diamond which starts at the bottom but actually protrudes all the way to the top, so that extra 500 protects against that really obscure example, I think. Yeah, whatever. Good problem, actually. That one kept us thinking. Oh wait, is that just part one? Oh wow, okay. But actually, yeah, that actually wasn't. Now that I look at it, this isn't exactly complex code for part one. All right. Part two then. Hopefully they'll just give us something nice, like just build on what we've done, but change some little thing. Because I think I will finish the stream after this. All right. On the other hand, if the coordinates are safe, maybe the best you can do is try and find a region near as many coordinates as possible. So we're doing the opposite way around. Well, okay, let's read. Suppose you want the sum of the Manhattan distance to all of the coordinates to be less than 32. So for each location, add up the distances to all of the given coordinates. If the total of these distances is less than 32, that location is within the desired region. I think this is actually easier than what we were doing before. No having to mess around with infinite or whatever, it's just taking this list right here and working within that list, never going to 1,000 spaces or whatever. I mean, okay, let's understand the example. So we've got these locations, A, C, D, E, B, F. Okay. Consider the highlighted location 4, 3. All right, that location there. So the distance to each, to A is that, to B is that, blah, 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 blah. Sum them up, we get 30. That's less than 32. So that location is kind of within the region. Within the region meaning it's safe. Yeah. Wait, but... Okay, we're still ranging over the grid. But we can probably use a smaller bounding box this time. Just go from 0 to 500, because surely... Yeah, anything within that box going outside that will probably be more than 32 to some coordinate, so yeah. Oh, damn it. They're not going to 32, they're going to 10,000. Yikes, okay. Ooh, alright, Ah. So... What is the size of the region containing all locations which have a total distance to all given coordinates of less than 10,000? What is the shape of the resultant location? It'll be kind of like a big diamond, won't it? Except not quite. Along the edges, it will have a... Hmm. So really, we would just want to find the boundary of this, all the coordinates which are exactly 10,000. And if we knew that, then everything inside that boundary would also be less than. And that boundary is probably convex. Okay. So this probably actually requires more thinking than the first part. Um, so if we look at this example, it has a shape which is sort of like a sphere, a disc. But it wouldn't really have that shape, would it? Oh, hang on. So what happens if we go? Okay, look at that space there. What happens if we go one space up? We add one for every location we're moving away from, and we subtract one for every location we're moving to. In this case, we're moving away from C, D, E, F, and B, and we're moving towards A. So if we were to go there, we would add 1, 2, 3, 4, 5 to the distance and remove 1. So we would add 4 to the distance overall. So that's why that would happen. So what does that mean? Well, that's how we would find the boundary. Well, so if we were to form a bounding box which is just like this, it's just basically contains these, right? That would be basically 0 to 500. And we can look at all the spaces within that. So if we are in any space outside that, then every time we move one space further, we are always adding 1 for every location. We're moving away from every location simultaneously. No, not true. Yes, that is true. As long as we're moving out away from the box. So that would add 1 for every one of these. So so that would help us find the boundary. Once we find the boundary, because we can start with our boundary being the box, but keep pushing it until we reach all the points which are exactly 10,000. Well, not exactly 10,000, but just outside. The furthest points whose sum gives us less than or equal to 10,000. That would be the boundary of the shape. I think I can compute that without too much difficulty. Then what? So it'll probably look like some sort of sphere. I don't know what the shape will look like. Because that looks like a sphere. Yeah, it would be because... And then once we got that, we can compute the area using... how do you compute the area of a convex shape? Some sort of method, I don't know. So is that... If I split it up into those stages, is that doable? Music stopped. Probably a long time ago. Oh man, I'm quite hungry as well. I might need to save part 2 for next time. I don't like to stop in the middle of a problem, but this looks like a bit of work. No, is there some clever method here? It's like, is this sphere like the intersection of some... Yeah, so that process I described, I think I can do that. Let's put it this way. For every column, I can work out what the top and the bottommost points are, which are within 10,000. just the top point and the bottom point. For every row, I can do the same thing. I can find the leftmost point and the rightmost point. That allows me to draw the boundary by using that process. Okay. So that's stage 1. I can draw the boundary. I can have a list of points which form the boundary. Stage 2 is calculate how many spaces are within that boundary. Is there a quick method of doing that? Computational geometry. Find area of convex shape. But this shape is not defined by... No, it's integer points. It's not... Find number of integer points within convex polygon. That's sort of what we're trying to do. We can test if a point is inside a convex polygon. That's a standard algorithm. So it's a question of... I think I'll save this for next time then. I'll give me some time to think about it as well. Seems like an interesting problem. You wouldn't normally need like advanced geometrical knowledge for this, so it's probably something simple. Like, see, that looks like a nice sphere. So it's probably just... It could just be literally just a sphere with center so-and-so and radius so-and-so. Can I show some mathematical argument why it must be a sphere? But I don't mean a perfect sphere, I mean like a Minecraft sphere. Like, can I prove some reason why it must be the Manhattan sphere, i.e. it has a center somewhere and all the points are within distance of that center? Because, yes, is it? That might be true. Because why? It's something to do with this argument I had where you move one space and you strictly increase the distance to every location by a certain amount. See, there's two of these locations inside the sphere. 4 are outside. Is that significant? And how many are there altogether? 1, 2, 3, 4, 5, 6. And 32 is 2 to the power of 5. These are all interesting numbers. Yeah, I have a lot to think about. Alright. Leave it there then. Yeah, I feel kind of dumb about that part 1. That was way overcomplicating the problem, but we've learned from that experience. I'm pretty sure there's some really nice, smart argument that could be described to someone who doesn't know much geometry explaining why the answer to this is really straightforward and just it's some sphere with so-and-so and radius. I can't think from the top of my head what it is, but I mean, I studied computational geometry to like PhD level, and I remember it usually was the case that a lot of these complicated looking problems, usually it just ends up being, you know, it's just some convex polygon which looks like this, or some nice sphere, or some rectangle. That's why geometry was often studied by, you know, some of the great mathematicians like Plato and so, because it had so many beautiful symmetries and simplicities and stuff like this. Euclid. Last time I left off in the middle of problem 6 because it was not... It wasn't actually tough. I just got stuck down the wrong path for a long time. So let's try and finish problem 6 off. So I'll need... Okay, so let's have a look at 6 again. So we have these points in 2D space. And we're trying to find count how many points, how many spaces in 2D space, how many coordinates are within 10,000, strictly less than, so less than 10,000 distance from all of those spaces. No, the sum of distances from all of those spaces is less than 10,000. Ugh. So I've had a brief think about it, and I think there is a way. So this space of points that we're looking for, it's a convex space. Alright, it's probably going to be some weird rectangular shape, but it's going to be irregular, probably. It's not a perfect square, it's not a perfect circle, it's like this. These hashes here, they're forming a weird rectangle, but it's kind of growing outwards. So my idea then is to find the leftmost point. It'll be off the edge of the map. The furthest most point, which is within 10,000. So it'll be kind of in the middle row, the median row, because if you pick the median, then if you go up or down from the median, you never decrease the distance. It's easy to show. Alright, so find the leftmost point. Then I'm going to go from each column by column, starting from that point. Find the highest and lowest points that are within 10,000. Right? If I do that, and just keep going from left to right, if I knew what the highest and lowest points before were, then in the next column, the highest and lowest points should be off just by 1 at most. Like, you can never jump 2 spaces, can you? I don't think so. So we do that. We just go from left to right of each column, finding the highest and lowest spaces. And if we know that, then we know what then we can find out the number in between. Hello, DIJ. How goes the coding? So I've just begun, well, on part 2 of this question 6. had a brief think about it offline. I think I have an idea for how to do this. It's a bit messy because I don't think this space that we're trying to find is a regular shape. So it's not like it's a square and we could just multiply the sides together or whatever. And it's not a sphere either, which would also be easy, even though this looks like a sphere. So I think, let's try and code this. So that was part 1 there. Right, now we do part 2. So we don't care about any of this really now. We've got the locations. So we probably need some helper functions. Let's say let's define a method. Oh, let me zoom in a bit. Okay, define, let's call it summed d, a summed distance for a given position. That would be, I just remembered. Is the coding game competition started yet? I didn't hear anything. Because that's something else I'm going to stream, but somebody came into chat and reminded me a few days ago that it will be starting soon, so oh, I have to log into the site again, hang on. Oh, damn it, now I need to log in and I'll have to sort that out another time then. Oh, we don't need to log in to see what is coming up. Oh, it's already started. No. It starts on the 12th. Okay. Alright, we've got 2 days time. Wait, what? It starts on the 12th and ends on the 14th? It's only 2 days long? Oh, it's one of those short puzzles competitions, not a proper tournament. Alright, let's get back to the task at hand. Alright, so we want sum of os, so it's going to be absolute os 0 minus loc 0 plus absolute pos 1 minus loc 1 or loc in locs. That is the summed distance. So as an example, we can try printing summed d of 0, 0. Oh, we're still running part 1. Can we just stop that? Let me just even out these. All right. So summed d of 0, 0 is 20,006. suppose that makes sense because this 0, 0 is actually quite far from all of them. Let's pick something a bit more midway. We want to find a place where they're actually... It's actually kind of short distance. 8918. So that's just not... That's not... That's, I mean, that's quite close to 10k, but okay. So somewhere in the middle... Oh! Wait, so if we go as far as 0, 0 and we're already exceeding, then maybe I was overthinking this. Maybe you literally just count up all the spaces and sum their distances. There is a smart... I was trying to think of a really smart way of constructing the boundary of a convex shape from left to right and then summing the individual column heights, which is some proper computational geometry stuff, but maybe I'd just do the brute force then. So what would I do? I would say... So the total equals 0 for x in range. Brute force is always the right answer. Almost always. You can come up with problems which even brute force won't solve. Sometimes. Kind of like optimization problems. For which you have no measure of correctness. But yeah, when you're searching a search space, and you have some measure of correctness for each element of said search space, then yeah, brute force usually can solve everything. So we just want to... Okay, let's just go from 0 to 500 then. This might not be wide enough, but then we can widen it. It's not that big a deal. If summed... So basically we want to say total plus equal summed d of x, y is strictly less than 10,000, not less than or equal to. So that's it? 39149? I might widen it a bit because we can afford to go wider here. So let's go minus 500 to 1000. That's really wide, but let's just see that the number doesn't change. So that's 3 times wider, so it's square that, it's going to be like 9 times, take 9 times longer to run. 39149. So that's it. Just those 3 lines, basically. Damn, and I thought I was being clever. Well, I mean, I think my method would work for a part 3, like where you just where you increase 10k to like 10 million or something. But it's understandable because these problems are meant to be approachable to anyone with a basic mathematical understanding, and I think what I'm doing is using advanced understanding of computational geometry there, which maybe is beyond the realm of like what they're going for with this website. But sometimes they do push it a bit. Let's try it anyway. Correct. Wow. So you know what? Actually, that problem, 6 overall, is actually quite easy. I just made it way more complicated than it needed to be. Both parts. But that's, I mean, that's sometimes the problem. Sometimes you gotta know when to rein it in and think, am I overcomplicating this? Is there a simpler solution? Given the nature of this competition. It's problem 6. I mean, sometimes you can have hard problems early on, though, so... Okay, we're on to 7. Ancient Nordic Elvish. Ooh, graphs. Looks like a graph problem. Okay. You find yourself standing on a snow-covered coastline. Apparently, you landed a little off course. The region is too hilly to see the North Pole from here, but you do spot some elves that seem to be trying to unpack something that washed ashore. It's quite cold out, so you decide to risk creating a paradox by asking them for directions. Oh, are you the search party? Somehow you can understand whatever elves from the year 1018 speak. You assume it's ancient Nordic Elvish. What is this link? 2015. Ah, they mentioned ancient Nordic Elvish. We've got lore developing here. It's in the 2015 they first mentioned ancient Nordic Elvish. See, this is why you've got to play all the years. Then you know all the lore ready for next year. Could the device on your wrist also be a translator? Those clothes don't look very warm. Take this. They hand you a heavy coat. Gotta get that Deep Santa lore. Yeah, exactly, because every year the competition, some problems, they mention things from previous years. Normally it doesn't matter, it's just lore. But once or twice it has actually kind of built on a problem that was done before. So if you had done that problem before, that helped a huge amount. Especially those assembly code programs, which a lot of people hate because they're very difficult a lot of the time. But we do need to find our way back to the North Pole, but we have higher priorities at the moment. Where exactly is the North Pole right now? Because the North Pole, the magnetic North Pole, shifts, doesn't it? Like, over a period of how many years? The North and South Poles move across the Earth, and then they swap places. So the South is at the top, and North is at the bottom. And then they swap again. So they rotate. But the actual North Pole is somewhere in Canada right now, isn't it? Because it's moving. Just because of the way magnets work or something. So I think you can actually just go to the North Pole somewhere in Canada. But I don't think it's near any civilized areas. The North Pole is, yeah, I guess it mean. What do people? Are there two meanings of the phrase North Pole, or does North Pole just flat out mean the top part of the world? But yeah. We do need to find our way back to the North Pole, but we have higher priorities at the moment. You see, believe it or not, this box contains something that will solve all of Santa's transportation problems. At least that's what it looks like from the pictures and the instructions. It doesn't seem like they can read whatever language it's in, but you can. You can. Sleigh kit. Some assembly required. Sleigh? What a wonderful name. You must help us assemble this sleigh at once. They start excitedly pulling more parts out of the box. We usually navigate based on magnetic north, not absolute north. When we talk about north, yeah, definitely, because that's the only way compasses would work, yeah. So the magnetic north, is it actually on land in Canada, or is it in the sea? Like, can you actually go there and walk around in a circle and have your have your compass point to it? Or would it just spin around in circles like on Minecraft when you're in the nether? The instructions specify a series of steps and requirements about which steps must be finished before others can begin. Okay, we got a dependency graph. C comes before A, C comes before F. Okay, that's easy enough to pass. So you create a topological order, basically. Okay, I've dealt with these before. Your first goal is to determine the order in which the steps should be completed. If more than one step is ready, choose the step which is first alphabetically. Oh, we are literally, we are computing the topological order. This is a thing. Not the physics one. Topological sort. So the algorithm used, the algorithm I'm familiar with, Kahn's algorithm. Never heard of that. I use this one here, depth first search. You search backwards from the E. Depends how many nodes we've got. If it's only a few, then okay, that's a fair few. We can't just brute force this. A brute force in this case would be try all permutations. That would take too long. Okay, nice. It's a classic algorithm. But I haven't done it in a long time, so it'll be good to work through it again. This is a classic, like, interview problem question. Because that's what companies care about, right? Testing whether you can do a topological sort, which you'll then never need to do on the job ever. And even if you needed a topological sort, it wouldn't be recommended to write your own. You would use some library made by some guy on Git who's had lots of code reviewers and forks and stuff. So that would be more trustworthy than something you write from scratch. Right. So first we want to. We want to create a directed graph. So the graph. Okay. Well, let's say class graph Okay, so we want to read the input. Line and have to read lines. Tokens equals minecool. Welcome. Oh, you were just doing Advent of Code 2018. Nice. How far have you got into it? Or have you finished the whole year? Only day 4. So I was doing day 4 like the day before yesterday, so not long ago. What was day 4? Oh, the guard duty. That was an interesting problem. That was one of the problems which seems like it's going to be way more complicated than it really is, as well, as long as you make some simplifying steps. Cool. You only individually day 4, or did you do 1, 2, 3, and 4? Alright, so I guess 1, 2, 3, and and working on 4. Okay, nice. Okay, so let's line.strip. And what language are you using? Python? Dot split by spaces. So you want Golang, okay. The example input gets the correct output, but not my actual input. Yeah, that's the worst case, isn't it? Then you're stuck trying to debug it yourself. You're not getting tripped up by those, because some of those timestamps start from before midnight, don't they? Like 11:48 or something like that. Which could catch people out. But I think that was also in the example, so... Alright, so we've got... token 0, token 1, okay. So I want... They always sleep during the 0th hour. Do they? I can't remember how it works now. Because you have guards that begin a shift. I don't think that's true, because in the... Oh, sleep at some point from... Oh, yeah, you're right. Yeah, I thought what you meant when you said that was they sleep at 0000. They are asleep. No, you mean they... Okay, yeah, you meant they fall asleep at some point between 0000 and 0059, essentially. Yeah, that's correct, yeah. Alright, so we want a default dict here. So we want to use default dict on a set. So map each letter to a... So graph.edges tokens 1. We add 0, 1, 2, 3, 4, 5, 6, 7. 7. Alright, so that should populate the graph. I can try printing it. It's making lots of typos here. So we've got L comes before BAPK. Is that correct? Probably. We've got lots of things here. Okay. That's step 1. We've got the graph. Now we could actually solve this the really slow way, the quadratic way. Just because we've got 100 at most, we've got 100 letters, but actually fewer because it's at most 26 because there's only that many characters. So actually we could just, instead of using topological sort, we could just use some quadratic approach here. Just every so how do we do this? So we're not going to bother using the clever algorithms, which would be depth first search. I think you run it backwards through the graph, starting from the letter, the node which is furthest ahead in the graph, so it has the most dependence, the most nodes that come before it. But we don't need to do that. So let's say order equals that. So let's say we have a bunch of letters to put into this order, and they're going to be, let's call them nodes. Graph.edges.keys. Okay. Just make it a set. Okay. While nodes. So while we still have nodes, we're going to look at them, pick the one which comes earliest, and put that in order. And when we put it in order, we remove it from nodes, but we also have to... Yeah, okay. So we'll have to delete it from the graph as well. That's fine. All right, so while nodes. So we're going to take the minimum of nodes. E equals lambda so we take a letter. So how do we minimize this? We want to take the... We want to pick a letter that doesn't appear in any of these sets. That means nothing comes before it. So it's viable to pick that. So how do we express that? We want to say, we want a Boolean. Which is Not any L in S for S in graph dot edges dot values. So the values are all these sets. Each value is one of these sets. We want L to not be in any of them. Or actually we could rephrase this as all L not in S. Okay. So that'll be 0, 1, and 0 is better. So we're going for the 0, which will always exist. But we want to break ties on the letter itself. So we want the first letter in the alphabet. So we should minimize this pair. Okay. First is that when we find first, we end first nodes dot remove first and graph dot edges delete graph dot edges first. Remove it from the graph. So by the end of this we should have an order, right? What do we want in the end? Just to print out the order as a group of letters, okay. So this is quadratic time, which would normally be slow, but for this it should be fast enough. What the? A, B, C, D, E, F, G, I, J, K, M, N, O, P, Q, R, S, T, U, X, Z, H, L, R, V, W. Interesting. I don't think that's correct. A can't be first. Look, A has a dependency. So why is it picking A first? You found the bug, Michael? I was adding 1 for each unique minute a guard has slept instead of total minutes. Oh, okay. Oh, I see, yeah. Because they sleep multiple. On that particular minute, they may sleep multiple times, just at different times. Oh, what's gone wrong here? Is my logic here correct? Let me try this. So I want to print just A, not in S for S. So that should say false. False, correct. Does false come before true? False is less than true. Should be. True. False is less than true. What is the minimum of false and true? Should be false. Is this all basically like zeros and ones? False. So A hang on. Oh no, wait. No, something's wrong here. Got it the other way around. I want the trues, not the falses. So I want any. Any L in S. So if A is in any of them, it will be true. But I want the one which is not in any of them, so I'll get the falses. Let's try that. There we go. That looks correct, because L, I think, would come first. I didn't see L in any of these sets. Yeah. And it's sorting them alphabetically. And A, after we've removed L from the graph, then A becomes viable. So that looks plausible. Damn it, it's wrong. Alright, let's test the example. Welcome back, TJ. Alright, I've had a wrong answer. Let's see if we can debug this. So for the example, we've got ooh! So we're just missing the last one. Why? Oh! E is a letter which exists, but it's not in any of these left-hand ones. It is in these right-hand ones. If we want to know what all the letters are, we have to take the union of all these left-hand ones and all these right-hand ones. That's the only way, because it might mention one in the left only, it might mention one in the right only. So if I want to know what all the letters are, I've got to make some global set here. Alternative, no, well, yeah, we'll make some global set here. And do nodes.add tokens 1, nodes.add tokens 7. That should give us all nodes. Now take that one out. Now test it. Yeah, and now we need to do if first in graph.edges, because it might not be in the left-hand side of the graph anyway. And delete it. Abdeve. Okay, good. Alright. Let's go back to that. Oops. Alright, so it's slightly different from before. because we've got the Y now. Oh, I should have noticed that the Y was missing, because Y is like the tail end. I noticed that, but I didn't see it in the string. But that's a problem. Correct. Part 2. As you're about to begin construction, 4 of the elves offer to help. The sun will set soon. It'll go faster if we work together. Now you need to account for multiple people working on steps simultaneously. If multiple steps are available, workers should still begin them in alphabetical order. Each step takes 60 seconds plus an amount corresponding to its letter. A equals 1, B equals 2, C equals 3, and so on. So step A takes 61, Z takes 86. No time is required between steps. To simplify things for the example, however, suppose you only have help from one elf, and that each step takes 60 fewer seconds. Don't simplify things for the example, that makes it different. Then using the same instructions as above, this is how each second would be spent. Okay. Alright, fine. So worker 1 is working on C. The second elf can't begin on the same letter, so worker 2 has nothing to do. So worker 1 has to work on C until it's done. Fine. Then we have 2 nodes available, so we put worker 1 on A and worker 2 on F. This is where it gets tricky, because you have to make a choice of where to place the workers. And it's not gonna always be obvious, because you have to look down the line and what will help things. Doesn't matter. If there's work to be... You got the test case right and the input wrong again. Yeah. That's annoying when that happens. Wait, but the one thing that really... Mindcool, thing that really differs between the test example and the input is that the input is in an arbitrary order, isn't it? Whereas the test case is... It's weird hearing the song. Oh yeah, that song comes up in... Okay, so... Could I just... So the thing is, we want to avoid situations where one of the workers has nothing to do, because then we're losing time, essentially. There's a fixed amount of man hours, man minutes, or whatever, man seconds in this case, that needs doing. So the best optimization we can do is have both elves working at the same time, but they can't always do that. Because, okay, this happens here. At this point... Completely derailed. Well, I don't have anything else to add to that other than that I remember that that guard problem, the input is in a completely arbitrary order, so you have to sort it first, whereas the test example was in chronological order. So that's one thing that's majorly different. But you may have already handled that. So we're trying to find the minimum amount of time it would take to... to complete all steps. Okay. Oh! No, we're not trying to find the minimum. If multiple steps are available, workers should still begin them in alphabetical order. Ah, so there's no choice to be made here. So worker 1 has to pick C, because that's the first available. Then, when we get to step 3, we have... A available. So worker 1 has to go to A. Oh, I see. Oh, okay, fine. So actually... Actually, this is just a simulation. We have to just do exactly what they say. We don't get to choose different orders. We have to pick the next available letter in order. Okay, so this is easy then. There's no decision process. We have to just do exactly what they say to do in that order. If there is a choice to be made between several different letters, choose the one which is currently available and lowest alphabet, earliest in the alphabet. And then we just count how long it takes. Okay, fine. Oh, but we've got 5 workers. Fine, we can deal with that. 60-second step durations. Okay. See, the problem is I messed up my graph here. It's not good practice, so... Somebody's singing in karaoke. Don't know if that could be heard. He wants me to leave 2 blank lines. That's I don't like leaving so many blank lines. Pep 8. 2 blank lines after class or function definition. There are 2 blank lines. Oh, after this. You know what? Screw it. I don't care about this. Pep 8. Right. So I gotta unmess my graph. So either way, alright, you know what, just make a fresh graph. I don't, because that was part 1. Alright, so we've got the order, we've stored it, because that will be useful. So we just have to do this again. Just to create the graph again. Create tokens, nodes again. Alright, so what have we got? We've got time. Time equals 0. Second 0. We've got a bunch of workers. Right, 5 workers, exactly. And they're all not working on anything right now. So for the first second, which is second 0, we need to decide who's working on what. That music's singing is really loud now. Okay, so how do we do this? Okay, so we want 4. Okay, don't set time equals 0. Just do 4 time in. Oh, I'm gonna use this cool thing. What's it called? The infinite sequence. How does it work? We want. I think it's iter_tools. iter_tools.count. For time in iter_tools.count, we need iter_tools. I have to clean up my code, starting with renaming the variables. Placeholder 1, placeholder 2. I haven't really... I never bothered cleaning up any of my codes. I mean, I figured if I were to put them on GitHub or something, I might clean them up, but never really did that. Though I might consider doing that though, but I won't bother cleaning them up. I'll put the code exactly as is. I like it to be a kind of like a record of what I did and what it looked like when I made it. Print time. This is just gonna count infinitely. Let's test this. Yep. Okay. That's cool. Alright. Wait, does it start at 0 though? Did I ever become a early 2000s millionaire? Yes. Day before yesterday, I finally beat that godforsaken game. It was a good run. There were quite a few questions I knew the answers to from past runs. The final millionaire question was one which came up before, which was which year did Monet die? And it was 1926. I remembered that one because it was the latest of all the years they gave. We had the question about woodruff again, which is something that came up before. Woodruff is a herb. So yeah, I am now on to Who Wants to Be a Millionaire 3rd edition, which is, I think, only came a year later because it was a really hot topic back then. Like, they were just churning out as many games as they could, so 3rd edition, I think, is still a PS1 game. I just want to see, we start at 0, do we? Yes, we do. Okay, good. Alright, so we've got a time. So. Woodruff, isn't he the protagonist from one of those really weird 90s point-and-click adventure games? Woodruff. Doesn't ring a bell. No idea. Okay, so what do we do in this count? We want to... So at the end of this, whatever we're doing here for this time... No, hang on. If we get back to this array of nuns at the end of this process here, so we do stuff, and then we check if all Woodruff and the Schnibble made by French people. Woodruff and the Schnibble. That's the name of the game? Never heard of it. Woodruff and the Schnibble. The Bizarre Adventures of Woodruff and the Schnibble. So if I had played it, I would have known the answer to that. Actually, I wouldn't, because it's just his name. I probably wouldn't have realized he's a herb. I feel like I should play it now, just in honor of that question. Was it in French? Is there an English version? Yeah, looks like there is an English version. Cool. This is the red light district where so many young Uzuks come. Okay, so you get to visit the red light district. I quite like the graphical style of this game. It's a little bit like Microsoft Paint, but it does actually look quite good. Alright. Focus. If all X is none for X in workers. Break. So that means if we it's by the same people that made Goblins. The series is just called Goblins? I don't know this one either. Series Goblins game. Or do you mean Ghosts and Goblins? Goblins Quest? Ah, Goblins with 3 eyes in it. Wow, there's so many more adventure games than what I've ever come across. I realize that. There's like, it was quite a... Adventure game was quite a big scene because it was like easy to make them. And get quite high returns because people get stuck on the puzzles for so long. It's like you actually get more gameplay out of them than you do if you're creating like a shooter or something, because you just have to spend a relatively small amount of time making those levels and puzzles, and the users spend a long time trying to solve them. So it's like you get a high return for the amount of effort you put in making them. And a lot of people made fan content and amateur games because there were like good tools available to do them. Adventure Game Studio was a big one. And it was a good avenue for people who wanted to practice their creative writing as well, so... I gotta play more of them. So at the end of this... print time, I guess that will be... the final answer. Alright, so the do stuff bit is the main bit here. So 4 P in, okay, so let's say for I P in enumerate workers. So there's 2 cases. If there is a none in this array, then that worker has nothing to do. We need to give him something to do. And do it. For 1 step. And if he has something to do, then we do that for 1 step. So I need a step counter. So I reckon when we put things in the workers list, it shouldn't just be a letter telling them which letter they're working on. It's got to be a pair, the letter and the number of steps. So let's say if P is not none, that means he's already got a job to be doing, just do it for 1 step. So we want to say the letter and the steps equals P. That P is going to be a pair. We want to decrease steps by 1. Okay, so we do that. Let me think about this a second. So Yeah, okay. So, by the way, down here we want time plus 1 just because we started at 0, so that'll mean the amount of time we've spent, not the time. We're sitting on. Alright, so if steps is 0, that means we've done all the steps necessary for this task. So we now give workers I equals none. So he now has no task. So next second, he'll be assigned a new task because he's now got none. Okay. Else, we just give him back that that task, but with fewer steps left on the clock. So equals L. There'll be L steps. You know what? The letter doesn't even matter. No, it does. Okay, yeah. Okay, so that's if he has something to be doing. That's the easy bit. Else, if he doesn't have something to be doing, we have to choose something. So we have this order, and we don't get to stray from this order. We have to use this order. But the first thing in the order might not be doable yet because it might be waiting for a different task to complete. So we have to go through the order, find the first letter in that order, which is right now available. Okay, so for task in order, if hang on, before we do anything, if there's nothing left in the order, so we have to say if order first. No. The best way to catch all issues here is do as normal for task in order. And if for some reason we go through this list of order and there's nothing suitable to do, that's possible, I think, because he's still waiting for something to happen, then this will be left as none. Hang on, something's not right here. We could end up with... there's a bit of a race hazard problem here. Damn it. Yeah, there's a timing issue. Okay, the problem I'm seeing is that if we deal with the first workers in the list, give them tasks to complete, make new tasks available, then by the time we get to the final workers in the list, we might have made new tasks available for them to take up. But that's not allowed, because they're doing this simultaneously. We can't let workers later in the list benefit from the earlier workers in the list having done their steps first. We've got to do it as if it's simultaneous. So if a worker finishes a task and makes new tasks available, those tasks are not allowed to be available yet until the next second. So how do I do this? I need to first make a first pass take all the nones and turn them into tasks. Then, as the next phase, have everyone decrease their steps. That avoids any new tasks being given to workers in the middle of this iteration. Okay, this is really confusing. Okay, I think I know how to do this. So the first phase, let's say phase 1, give tasks to workers who have no job. Okay. And then phase 2. Work on all current tasks. That means decrease the step count by 1. Yeah, that's safe. And if we do that in that order, we don't get that situation, I think. Alright, so, and then, after you do that, this is not quite correct either. Okay. After phase 1... No, hang on. After phase 1, if we've given everyone a task and then we see that no one has any tasks, that means we're done. We don't put this after phase 2, we put this after phase 1. So we give everyone a task to do. If nobody has a task, that means we've run out of tasks. We break that. Alright, so let's finish off phase 1. So we go through each of the workers. So if P is none, let's get rid of all this. Let's just say we want to say you have no tasks, so we need to find a task for you. So for task in order. Alright, so we go through the order. We look through the tasks. We pick the first possible one, the first task that is possible for this guy to take on. So what does that mean? That means we have to make sure that it's not in any of these sets here. It's not waiting for something else to be done. If all task not in V or S in graph dot edges dot values, that means task is not in any of these sets. That means it's not waiting for something else to be done. Then we're giving you that task. So we say number of steps needed to complete this task is 60 plus, that's going to be odd of that minus odd of A what did they say? A is 1, B is 2, C equals 3. Okay, so then we need to add 1. That's the number of steps they said is how we're defining it to complete that task. So we say workers I equals, so it's going to be task along with those steps. Now the important thing is we need to take this out of the order. So when we've done that, we break out of this for loop. Okay. And now if P is not none, we're confirming that the above thing actually happened, because maybe there were no tasks available. So if we have found a task, we now need to remove it from the order so that no one else tries to do that task. So order dot remove, hang on. If, no, not P. If workers I, we now have to remove it from the order, and we have to remove it from the graph. I can do that here. All right, I think that's the whole phase 1 done. Now phase 2, work on all current tasks. This is the easier phase. So we say, if you have work to do one step of work. All right, so we go for IP in enumerate workers. If P is not none. So we unpack. So we say task steps equals P execute one step. Now if steps is now 0, you've got no more tasks. So we just say workers I is now none. Else workers I equals, wrap this up again, task with the new steps. Okay. Is that everything? I don't feel confident with this. 437? Now, is it actually time plus 1 or is it time? This could be one off by 1. Let's try this. This is what I think it is. 437. Not right. Too low. Okay. We're gonna have to print what all this looks like. So oh god, have I? Oh no, that's fine. I thought I had it on the browser all that time. No, I just put it on the browser now. Okay. God, this is not going to be easy to debug. So So we can test it on the example. So we can say num workers equals 5. And 60 is the special, so the offset equals 60. So if we want to test this on the example, that's the example. And we want offset to be 0, num workers to be 2. Try that now. 13. And the correct answer is 15. Not far off. Now, it could just be that the actual correct answer is just +2, and for some reason I'm 2 off. Let's try and debug it first. So after this, we would just want to print workers. So after the first second, worker 1 has C, and he's got 2 steps left. That's correct. Then, aha! So this is wrong. Worker 2 has started B. He's not allowed to start B yet. So I accidentally... Okay, how do I fix this? So this graph mustn't be updated until that is finished. Not started, but finished. I've been updating the graph as soon as that task is started. That's wrong. It needs to be when it's finished. So here, right here is where we need to do this. So if this task is finished, we want to remove it from the graph, and we want to remove it from the list of... Oh, no. We do remove it from the orders there. That's correct. Orders just stops that task from being taken on a second time. Removing it from the graph enables new nodes that were waiting for that task to be finished. There's the distinction. Okay, let's try that. 16. So we off by 1 now. Print time, just time. 15. Is that correct though? Is that what I want? So we're saying print time along with the workers. So at 14. Ah, yeah, because we break after the first phase. That makes sense. So on t equals 15. We do the final break. Yeah. Okay. Let's try this on the real thing then. Offset equals 60. Numwork is 5. Go. 936. Does that look about right? Y is the last thing to be finished. That's completely correct. Do we ever have all 5 workers working at once? Yes. No. they're not working at once, but we do still need all 5 workers because they're kind of rotating the work. Ah, there we are. They're all working at once here. This looks... Yeah, they are. 936. Whew. That was a good problem. That made me think a bit. It was harder than expected because it's one of those problems where they tell you exactly what to do and you're not allowed to stray from it, but it was still hard to actually code it up correctly. Like, I was worried it would be an optimization problem, which, as I mentioned before, is not actually solvable by brute force. You'd actually have to find a smart way to optimize. No, that is solvable by brute force if you choose every permutation, which would take too long anyway, but that's problem 7. I think it's time for me to make dinner, and that karaoke is getting louder and louder and louder. Hopefully they'll finish by 9 PM, but no idea. Yeah, I'm gonna go have dinner. Brute force is always the right answer, rarely the correct answer. Well, sort of the other way around. Correct would imply that it's mathematically correct, but right would imply it's the right choice to choose. So I would replace right with correct, actually. It's always the correct answer in that it's mathematically correct, but not right in the sense that it's the wrong choice of algorithm a lot of the time. And we're making a nice little hat here. Oh, is that a sleigh? But yeah, there's some interesting problems that can't be solved by brute force. They come up in like number theory sometimes, some things to do with prime numbers and cryptography. For example, there is a form of encryption which is used in the real world, which is unsolvable by brute force. Like, it doesn't matter how much time you have, it doesn't matter how powerful your computer is. If person A sends a message to person B with this algorithm, no person who intercepts the message can work out what they were saying. It's called the one-time pad. And it's intuitively quite simple to implement. I could, just using a pen and paper, create a one-time pad and communicate with a friend. You could even make this a smartphone app, and then you could communicate with them. And it's mathematically impossible to ever find out what that message is, if anyone were to intercept that message. Which is cool. And okay, this Wikipedia is making it seem way more complicated than it really is. It's based on the idea that, let's say you and your let's say you had a book, and your person B also has that same book. Let's say it's, I don't know, Jurassic Park or something. But let's say you've got the only 2 copies of Jurassic Park in the whole world. Then I could talk to you by saying, go to page 5, word 17, and take the first letter of that word. Now go to so-and-so, so-and-so. I could do that. And you are the only person who would know which letters those correspond to. Anyone who intercepts that intermediate message can never, even using brute force, no matter what they do, they can never work out what that message was, as long as you never reuse characters you've used before. If I were to reuse a word or a letter that I've used before, then it breaks. In fact, there's a very good Sherlock Holmes story where Sherlock Holmes actually cracks one of these codes where they reused letters, and he actually works out what it was because he says, okay, E is the most common letter in the English language. I see that E is coming up in this message. I see that this letter is coming up in this message a lot. That means it must be E. I can't remember which Sherlock Holmes story it was. It's one of the short stories. And from that, he actually worked out what the message was, and he was using frequency analysis. Is this similar to how people think the number stations work? Number stations. I don't know what number stations are. But yeah, so this is an unsolvable, uncrackable message. And that's what I find funny about all these excessive efforts that the government makes to kind of break phone encryption and break into Apple and stuff. The thing is, if someone really wanted to send basic messages to another person, they could just use this. They could just make an app. I could code an app which use this. So, you know, they're only... But it is true that a lot of terrorists or whatever, they use poor algorithms, and half the time they don't even encrypt, and those are the ones that get caught. But if I wanted to send a message to another person in another country and I use this, that message will get to that person and no one will read it. That's a mathematical fact. The ones who get caught are the ones who just don't use this. They just use... They don't really exist anymore, but during the Cold War, random radio stations would broadcast strings of numbers. It sounds like it's some sort of key. It's similar. It's probably not the one-time pad. The number one rule of the one-time pad is never broadcast your book, i.e. your copy of Jurassic Park in the analogy. Give the other person that book, you know, put it physically in their hand, never send it in the post, and that way it's secure. Good. But it requires the use of a single-use pre-shared key. Yeah, exactly. This is the reason no one uses one-time pad in like high-frequency message transmission, is because the key is as big as the message itself. So in terms of storage space, that's just a waste of time. People want keys which are small, and for messages that are big. But I'm just using this as an example of one where the downside is your key is as big as your message. So that's, you can't send huge amounts of data over a long period of time, because you just have too much key space. But for basic messages, if you're just talking to someone and you wanted to say, I don't know, tell them the army will be at the hill at noon or whatever, then it'll work. So yeah, I don't really know why I went off on this tangent. Oh yeah, because it was an example that can't be brute forced. So yeah, one thing that can't be brute forced. What was that Sherlock Holmes story now? Sherlock Holmes frequency analysis. The Dancing Men. Yeah. So yeah, if you want to see that, the frequency analysis written as a story, that's one of Sherlock Holmes' adventures, The Dancing Men, where he cracks a message by frequency analysis. This is an interesting technique for breaking ciphers, and it's a very important one because a lot of ciphers can be broken that way, because, you know, E is the most common vowel, T is the most common consonant, and from that you can work forward and work out what all the letters are. Alright, so also, if anyone at home wants to be on my leaderboard here, that is the code. In fact, I'll post it in chat as well, just in case, but it will be there. So you can kind of join my leaderboard if you want and compare which problems we've solved. This leaderboard holds for all the years, so 2017, 2016, all of them. All right. Cool, I'm off then. I try to keep up with this every 2 days or so, with 1 or 2 problems. I'm trying to do all the years before Christmas because that's when, you know, the actual event will come up. So that means I gotta do 2019, 2021. I might have to spend a month just putting a lot of work in if I want to achieve that. I was playing Google's beginner CTF and they had a cipher section. Frequency analysis was mentioned. Yeah, I mean, it's a really powerful tool because it's very hard to avoid getting beaten by frequency analysis. All right. See you next time.